Thank you for coming. I know a few of you have seen me give a version or seen me give an introduction to trace ideals before, so I put a new kind of discussion in the front. But the basic idea is that I wanted to start with how you might encounter something called a trace idea, like as you're doing other work in commutative algebra, right? So we're going to start by positioning ourselves in a discussion about rigidity over domains. And I'll explain what this means, not in too much detail, but by talking about the Hünicke-Wiegand conjecture. So this is around 93, 94. And it says this. So R is going to be Gorenstein, local domain of dimension 1. M is finitely generated. And M tensor, M dual is going to be torsion free. Right, so these are our hypotheses. And I'm just going to say equivalently, M tensor M dual is reflexive. Also equivalently, x1 of M against M is 0. Right, so all of these are equivalent. And if you have all of these hypotheses, the point is that M is free. Is this too low? Okay, so this conjecture, so first of all, in this setting, these kind of three equivalent conditions is what we're calling rigidity. Specifically, this one is usually called rigidity, but in this setting, of course, all equivalent. And this conjecture is kind of linked to a number of other conjectures concerning rigidity in representation theory and commutative algebra. So the Alexander-Ruyten conjecture, Tachikawa conjecture, et cetera, et cetera. What I want to do is let you know that let's see the year. In 2018, Hünicke, Iyengar, and Wiegand got together to prove a bunch of basically versions of this under milder hypotheses. This is known in some cases, it's known for hypersurfaces, it's known for this, that, and the other. But in particular, I want to highlight that they proved in this paper that the Hünicke-Wiegand conjecture is true for ideals with the endomorphism ring of I, Gorenstein. So what I'm going to do is I'm going to give a proof of this in kind of a meandering way. It is a proof that does not exist in any paper, but it's kind of an amalgamation of things that exist in a multiple paper. And the reason for doing this is to explore how trace ideals might naturally appear when you're exploring this question, right? So in order to do that, first, I'm going to introduce some facts. So when I contains a non-zero divisor, then by, say, a non-zero divisor X, I'm going to tell you what this is. Say F is in this, actually, I have less space than I thought on each one of these. Let's do this. Say I want to look at I dual. I can think of this as fractions. Fractions in the total quotient ring that map I back into the ring, right? How do I identify this, which is just the homomorphism from I to R, with this set via this identification? And then I can also do the same thing for the endomorphism ring of I. We can think of this as things that just fractions that send I back into I, right? And so this same identification identifies Homs from I to I with this set of fractions. And the reason I want to do this is to make it really practical, right? You don't have to think about general homomorphisms. You can just think of these as literal fractions living in the fraction field, okay? And so what does this mean altogether? As I just said, I can think of the endomorphism ring living here as a finite extension of the ring living in the total quotient ring. I'm going to call this guy C. So armed with that, now let's start proving this. So this is a proof in 3 parts, 3 very small parts. So don't worry, this won't go on forever. To explore the idea of traceness. So part 1, the trace and rigidity.
Can we swap the board, please?
Oh,
thank you.
Okay. Part 1 is the trace and rigidity. So let's think about this important module. So this module and its torsion freedness is one of the key hypotheses in this conjecture, and it is equivalent to rigidity, right? So, so there is a natural map from here just by evaluation across the tensor to the ring, right? But because we're thinking about I living in the ring and I dual as living in the fraction field, we can just think of this as smushing, right? So I'm just going to multiply them in the total quotient ring to get I dual. Okay? And then over here, there's going to be some kernel. Okay. So we're going to localize at 0. What happens? This turns into a copy of the quotient ring. This turns into a copy of the quotient ring. This ends up being 0. What does that mean? It means that this guy was torsion. And because we assumed that this was torsion-free, this means that K is equal to 0. Okay? Okay. So what does all of that mean? Rigidity, in this case, means that I tensor I dual
Torsion-free.
torsion-free. Sorry, I can spell it out. Right, so we established that K is torsion. This guy being torsion-free gives us that it's 0, right? So what does this mean for us? It means that rigidity means that there's an identification between this important module and this guy. This is the trace ideal of I, right? Rigidity means that this guy is the trace ideal. Actually, let's use this space. Okay. I'm just going to insert a fact that we're going to use, which is not hard to think about. Here's a new term. I generates its trace ideal, I times I dual. That just means that there exists a surjection from copies of I onto this guy for some index set. There we go. Okay. Part 2 of 3. Trace ideals, conductors, canonical modules, and endomorphism rings. Kind of unwieldy, but here we go. Okay. All right, so remember, our center of our endomorphism ring, our endomorphism ring of I is Gorenstein then in this case. So what does this mean? That means that C is isomorphic to its canonical module, right? This, of course, is CR. Since R is Gorenstein, we can calculate the canonical module of C, and both of them have dimension 1, so we can calculate the canonical module in this way. And so let's just do some identifications in Hom tensor jointness. So remember, C is just Hom II. So that's how I get from here to here. By Hom tensor jointness, we get that this is the double dual of this tensor. Okay, this guy was reflexive. So it's isomorphic to its double dual. And as we've already established, that's isomorphic to that. Okay, so all we've done here is identified a whole bunch of things in the case where C is Gorenstein. So we've got the ring, the canonical module, I tensor I dual, and the trace ideal. And this is also defined, if you know this word, the conductor of this ring living in the total quotient ring. So here's the conductor. So all of these things are identified in this setting. Okay. What does that mean? So if we've got this surjection, which is isomorphic to the ring, this guy's a ring over here. Sorry, this guy is a ring over C. Sorry, it's a module over C. So this splits. Okay. And that means that I tensor I dual, which is isomorphic to I. Actually, yeah, that's fine. Is also rigid. As a summand of I, we've now transferred the rigidity from I to these modules. Okay. Any questions so far? Is that okay? Okay. So that's part 2. And what I will say here is that this relationship between trace ideals, conductors, canonical modules, and endomorphism rings, while we're doing it in this special setting under the hypotheses of the Hünicke-Wheaton conjecture, this is a robust connection. This connection kind of always exists, and we'll get into it a little bit later. Okay? All right, part 3. Last part. Kind of redundant. Trace ideals. More trace ideals and rigidity. Okay, so here's a fact. Here's the trace ideal. Its dual is equal to its endomorphism ring. And we'll talk about that explicitly later, but you can just take it as a fact for now. And here's what we can say. We can just set up this simple short exact sequence from this ideal to the ring to its quotient. We're going to map the trace ideal into the short exact sequence. And what do we get? We get the endomorphism ring of this trace ideal, then the dual of the trace ideal, then a Hom into this guy, and then of course the first text. All right, so we established here that this trace ideal is rigid, so this vanishes. By this fact, we have this identification. Okay, so what we get is that this is 0.
That's sort of obviously 0.
Sorry, which one?
The Hom.
Because this is 0 and this is isomorphism.
No, but why can't we just tell them, you know, mapping a thing to quotient by that thing? Why does,
Say again?
so when we, so I do all.
Oh,
anything-
you're asking why it's not always 0.
Why, yeah,
Okay, got it. So, for example, think of, sorry. So like, right? Okay. So, are we okay with this being a Gorenstein ring? 0-dimensional Gorenstein ring. So it has a socle, 1-dimensional socle, right? So in fact, any module should have a non-zero mapping into this, right? Does that, for example, including. So for example, in this case, this is a 1-dimensional ring. This is a domain. So this quotient has a socle, right?
I think that is stupid.
Oh, okay.
If we take comm of x squared into k squared x hot x.
Sure.
Doesn't the x squared just have to go to 0?
No. So-
What is this comm?
Over the expected ring. So let's just, okay, think about, okay. This is a good thing to struggle with. This is a good thing to clarify also. Okay, so let's just think of the structure of this, right? So this is a 0-dimensional ring, Artinian, right? Because we started with a 1-dimensional domain, 0-dimensional ring. So think of the minimal ideals in this ring, right? So there are copies of K. And any module over the ring has a non-zero map to those copies of K living inside the ring. Does that make sense? It's including this module.
So I guess we're mapping x squared to x.
Yes, in this case.
Right. Thanks.
Yeah, no, absolutely. This is a good thing to clarify, especially because now we're saying it definitely is 0, and this is special, right? Does that make sense, everybody? This hump?
That's an R. No, I think Soccer just saying doesn't the hump have to be over things, that's what I'm saying, and I agree. Yeah,
If it's sending x squared to x, like.
that.
Learning seminar.
Because like, this is just basic perfect to R, so we can just do that as comm R and,
Where is it sending x?
In this example?
There is no X, because we're generated by x squared.
Oh, you're taking the module x squared.
Yeah.
Okay, I understand.
Is that okay? Okay, awesome. So this is 0 for other reasons. But it shouldn't be 0 for the reasons that we just discussed. There's a K living here. There should be a non-zero map from here to here by virtue of that K existing. And so what we've actually concluded is that this has to be 0. We with? Is that okay? All right. So what does that mean? This thing that we've identified as our trace ideal is R. What does that mean? Well, I generates this, as we've already discussed. So that means I has a free summand. But it's an ideal in a domain. It's not going to have free summands. So that means that I is free. So as we, hopefully it's somewhere on the board here, right? So there exists this rejection. There we go. Yeah, excellent. Okay, so we've just proved this. Maybe not in the most efficient way, but not in too long of a way, right? But the whole point of this is, one, to show how the trace ideal kind of naturally arose in this exploration, right? Rigidity actually meant that we had the identification of I-tensor I-dual with the trace ideal, and then also shows different ways in which trace ideals behave. We've got this robust, as I'll justify later, identification with other kinds of objects that we're interested in. And we've also explored a little bit of the behavior of trace ideals. So here's the basis for an argument that trace ideals generally exhibit non-rigidity unless they're free, right? So there's a lot packed into this, and we have a proof of this proposition from the Hunicke, Wiegand paper. So with that, hopefully you'll now allow me to define a trace ideal more generally. Any questions on this? I'm going to start erasing. Is that okay? Okay. All right, and just for the record, I have no intention of getting through all my notes, so please interrupt and ask all the questions that you have. But trace ideals, the basics. Okay, definition. The trace ideal of a module M, we kind of suppress the in R, is you take all the homomorphisms from M to R, look at their images, sum up their images, that's your trace ideal, right? This I didn't realize, but over time, this notation has become controversial. There are lots of people in the room who work with trace ideals but don't like this notation. I stick by it because it's my original. Auslander did it, but also because it's kind of functorial in that if I were to take, if M was an ideal over a different ring S, and there was a map from R to S, then that would induce a map from the trace ideal of M over R to the trace ideal of M over S. So I kind of like this just to think of it as an operator, like something happening to R.
What's the other notation?
What is the other notation?
I can't see it.
Rebecca, what do you use? TR like that?
No, I still put M.
You put M down below?
And then the ring. That's
There's that. What do you use?
the tau, right?
Use the tau. I've seen it the other way as well. There you go. And then some people suppress the ring, you know. There's just other ways of writing it. Okay, but to finish this, it's also the image of the map M tensor M to R. That's evaluation across the tensor. It's another way of thinking about it. And as we said before, when I contains a non-zero divisor, this map just becomes a smush, and the trace ideal of R of I is just I times I dual considered as living inside the total quotient ring. Okay. So here are some questions. Given an ideal, can you tell if it's a trace ideal? I.e., there exists some M such that, given an ideal I, can you tell? Right, so I give you an ideal. Can you tell it's a trace ideal of some module? The answer is yes. So an ideal is a trace ideal if and only if it is its own trace ideal. So you don't actually have to go looking out all over the category of R mod to see if there's some module of which this is a trace ideal. You can just look at the trace ideal of the ideal you're looking at. And if it is its own trace ideal, then it will be the trace ideal of a module, clearly. Now what is left is, can we calculate that? Can we actually start with an ideal and then figure out what the trace ideal is? And luckily over in the settings that we like, Noetherian rings, right? The answer is very much a yes. So easy to calculate using Macaulay 2 from the presentation matrix. Okay. So I'm going to, this is a learning seminar, I'm going to do this in detail. We're going to actually work through this. But we're going to start with the theory and then do a real example. So we're going to start with a free resolution. So here's M, Rn, Rm, right? Here, I'm going to call the presentation matrix the matrix A, and that is going to be an N by M matrix. What I'm going to do is I'm going to dualize this. So here's M dual. It'll go into the dual of that, which is just another copy of R to the N. Here is going to be A transpose. Here is going to be R to the M. Down here lives the Auslander transpose, if you're interested in that kind of stuff. Then what I'm going to do is I'm going to start resolving M dual, and that induces a map from RT to Rn. So here's an N by T matrix. Okay, so the trace ideal of M is going to be I1 of B. So it's the ideal generated by the 1-by-1 minors of B, otherwise known as the entries of B. Okay, so that's the theory. Let's do an example. Example. R is going to be equal to, this is going to look scarier than it is, y squared minus xz, x squared y minus z squared, x cubed minus yz. This is isomorphic to k adjoin T3, T4, T5. We're going to look at the ideal generated by x and y. And I want to find the trace ideal of I. And I figure I'll put this on a different board. It's a workout. Oh my God. Okay. If you'll notice from up there, right, B is going to be in the kernel of A transpose, which is the same thing as the left kernel of A. So we can actually derive it directly from the presentation matrix, which is what we're going to do in this example. But it's the same thing as taking the transpose and then looking on the other side. Okay. So now let's start resolving it. Here's xy. I want 2 copies of the ring. Just project onto it to start my resolution. Then the cis versus G happens to be 3 generated. And here is A. I can't tell if this is a squared or a Z. I'm going to say it's a square. I don't know. Okay, so here's a resolution. Let's actually just figure out what the trace ideal of this thing is going to look like. So if I wanted to calculate the trace ideal using the definition of the trace ideal, what I'm actually going to be looking at is homomorphisms from here back to the ring. And I'm going to look at the images, sum them up, and that's my trace ideal. Okay. That induces, so this map alpha from the ideals to the ring is in correspondence with these maps, alpha bar, which is going to be like a 1/2 matrix, such that if this is A, alpha bar A is equal to 0. That's what we're looking for, right? Okay, in order to figure out what these maps are. And I'll just say that the set of things is generated by YZ, XY, ZX squared. So let me tell you what this actually means practically, right? So this here is the map that sends X to Y and Y to Z, etc. Right? Really hands-on. These are the things in the kernel, in the left kernel of A, or we could think of it as the kernel of A transpose. Okay, now just as an aside, in this setting, which is a domain, each of these maps are given by multiplication by something in the fraction field, as we said at the beginning, right? So we can actually also imagine these as multiplication by some fraction. And so, you know, in your head, you can just figure out what these are. This is multiplication by y over x. This is multiplication by 1. And this is multiplication by z over x. So those are the fractions. Okay? All right. Yeah, absolutely.
Not understand.
Sure, what's up?
Great question. But how can you tell if an ideal is a trace ideal?
Yes.
And the answer is yes, if and only if its own trace ideals itself.
Yes.
But then we can calculate trace ideals
Yes.
using this free resolution.
Yes.
I feel like, can this not be reverse engineered? Like you take B in this setting and you populate it however you want, you flippity flip it around, and you've got a presentation of M, which is the dual of the M dual that you get from the image of your favorite B.
Sure.
And then the entries of B make the tracing, right? Is this
So this is, so I'm hearing underlying your question is whether all ideals are trace ideals, because you can construct a B to just have the entries that you want.
Yeah. So is this B special sometime?
Excellent question. We know for a fact that all ideals are not trace ideals. And I'll just give a quick example of that, if you don't mind, because it's easy to write down. And in fact, when we finish this example, this will be another example of something that's not a trace ideal. Why is this not a trace ideal? Because this is isomorphic to the ring, right? So its trace ideal is R, right? So just kind of going backwards, we know that we can't do exactly what you were saying, but it's a good question. Like, what happens when we construct a B that you want, and then can you like define flippity flippiting?
Well, like take this presentation.
Yeah.
M, right? Like image of your, pick your favorite B.
Pick your favorite B.
And M,
Okay.
just call M for the image.
Yeah.
And then
What's this, a dual of something?
so you can't like that must be it. So you can't just dualize, you can't form the co-kernel won't be embeddable in a free module.
Not necessarily.
That's what's going on. Okay.
Yeah. Excellent. Thank you.
So if it is embeddable in a free module, does that mean you have found a B that can make a trace ideal?
If I'm understanding what that means, then yes. Yeah. Okay. So, but let's just finish this. So, you know, we've now like very hands-on, like calculated what all of the maps look like. And so this guy is going to be I1 of the left kernel of the presentation matrix, which is I1 of the matrix created by these guys. So YZ, XY, ZX squared. And then you just look at the entries. So this is going to be the ideal generated by X, Y, and Z. So what we have here, put a pretty explicit example of how these things are calculated. You can do it by hand. You can do it in Macaulay 2, especially for finitely generated modules over Noetherian rings. And then also this gives an example of something that is not a trace ideal because it is not its own trace ideal. So in this case, the ideal generated by X and Y is not a trace ideal over this ring. Okay. All right. How are we doing on time? 15 more minutes. All right. Let's see how far we get. Okay. The upshot. Okay, I think there's a natural stopping place coming up. So one, over a Noetherian ring, it's easy to calculate for M finitely generated. And so that means it's easy to test if I is a trace ideal. And two, it means also easy to characterize. Trace ideals. Here's what I mean by that. Trace ideals are the ideals in the ring that are stable under homomorphisms back to the ring. And so the endomorphism ring of the trace ideal, I've mentioned this before, but I'm writing this down in generality. Right, so the endomorphism of the trace ideal is the dual of the trace ideal. An I that has this property is a trace ideal. And this guy, because this guy is easy to calculate, that makes this easy to calculate, right? For example. All right, let's do some classes of examples. So we did a specific example. Let's do some classes of examples. So if I is an ideal with grade greater than or equal to 2, then I is a trace ideal. Now you're thinking, oh, that's a lot of things. It is a lot of things. Hi. But let's actually justify this. So 0 to I to R mod I. We're gonna dualize this into R. We're gonna get 0 R mod I R I dual, then this first X1. Because the grade is greater than or equal to 2, this is 0, this is 0. Everything in I dual is given by multiplication by something in R. That gives us this identification. Okay. So in large rings, trace ideals are ubiquitous. Okay. Another class of examples, if we've got an Artinian-Gorenstein ring, then the trace of any particular module is its double annihilator, and every ideal is a trace ideal. That is not obvious, but is true. Okay. In the interest of time, we can take a fork in the road here. So I can justify why it's called a trace ideal. Why is it called a trace ideal? or I can give you properties of trace ideals that are useful, maybe.
Useful property.
Useful properties, okay. Let's do some useful properties. Say again?
Just so that if you had said properties that aren't useful.
Oh, I mean, I'm proselytizing here. I might think things are useful that are actually not.
Domains where all ideals or trace ideals fields. So like just reverse engineering process. It's like asking is every co-kernel embeddable in every
The only domains with every. Yeah. Every ideal is a trace ideal. So Goto and some of his students a couple years ago proved that okay, there's a natural generalization from a trace ideal to trace module, or to just replace the ring with a module, right? And they showed that if you have a module that every submodule is a trace module in it, then you must be embeddable into a direct sum of the injective hulls of the residue field. So in a local ring, just the injective hull of the residue field. Let's translate that to our setting. The trace ideals are the trace submodules of our ring, right? And so we're asking, in which case is every ideal a trace ideal? It has to be embeddable into the injective hull of the residue field. So in this case, in the domain case, that would be Q of R. And so yes.
It has to be as embeddable as a submodule of Q of R.
Yeah. Am I quoting that correctly?
But isn't
Yeah.
every submodule Q of R over R?
Like not Q of R, Q of K.
Q of K?
Q of K. Yeah, so I did that wrong. Q of K.
For all residue fields.
Overall, so in the local case, only the one, right? And so you wouldn't be able to do that in a domain case,
Yeah.
right? Yeah. Does that make sense?
Yes.
Okay, awesome. All right. I probably should have written that down. Hopefully that makes sense to everybody else. Okay, properties. We'll do this quickly. Some properties. Okay, one, they're closed. So if you start with an ideal, I is contained in its trace ideal. And if you take the trace ideal of a trace ideal, you get that same trace ideal. Okay. So two, it behaves well under flat extension. So say M is finitely presented and S is flat over R, then we've got this identification. Said more simply, if I were to try and localize a trace ideal, I would get the trace ideal of the localization. If I were to complete, something similar would happen, right? Okay. 3 of 4, it detects the structure of M. So if R is local, the trace ideal of M is R if and only if M has a free sum end. Right, so this becomes a tool to detect free sum ends. In the non-local case, it just means that M has to be a generator in the module category. And then property 4 of 4, which is why you might want to move from all modules and then translate your problems into the world of trace ideals, is that it turns isomorphisms into equalities and surjections into containments. So here's what I mean by that. If two trace ideals are isomorphic, that means that they are equal. And more obviously, if two modules are isomorphic, that means that their trace ideals are equal. Also, if one trace ideal surjects onto another, then the first trace ideal contains the second. And if one module generates another, that means that there's some direct sum that surjects onto the other module, then the same is true. The trace ideal of the first contains the trace ideal of the second, right? None of these are particularly hard to prove, but these observations already allow us to do some pretty powerful things. So consequences, and I think maybe we can, depending on how much time we have, I could end here or on the next page. Got time? Consequences. Maybe there's probably a number of other ways to see this, but I thought that this was quite beautiful. This means that ideal isomorphism is a low dimensional phenomenon. What do I mean by that? If you got two ideals of grade greater than or equal to 2, they are trace ideals. They cannot be isomorphic unless they are equal, right? So if you have two ideals that are isomorphic in your ring, just by some mild observations about trace ideals, one of them has to be grade 1 or lower, right? It's a low dimensional phenomenon. So I'll just write that down. If grade of I and j are greater than or equal to 2, they are trace ideals. So I is isomorphic to j if and only if I is equal to j. Okay. Consequence B of 3. No, I won't do that one. I'm skipping to C. The trace ideal of, say, a canonical module determines the Gorenstein locus of R. What I mean by that is a prime ideal will contain the trace ideal of the canonical module if and only if R localized at P is not Gorenstein. And as some of you in the room know, like, people have taken this one fact and just run with it. There's right, there's like a gajillion papers like just taking advantage of this one use of the trace ideal, which you know, just relies on the fact that if you localize outside of this, then the localization of this is going to be free. And therefore your ring is going to be Gorenstein.
You have a Gorenstein ring.
Yeah.
None of the localizations are not Gorenstein, so your trace ideal or your canonical module is the whole ring.
Because your trace side, yes, your canonical module has to be isomorphic to the ring.
No.
Yeah. And so its trace is the whole ring. But yes, you backed into that. Perfect fact, yeah. See, so useful. Okay. All right. So now I'm going to highlight a bunch of open questions and also some partial answers to those open questions and some like very active areas of research using just basically the facts that we've described and some simple questions. And I think I will end after that because it is a good stopping point. So mostly open questions. Okay. So question, what does a trace ideal detect / determine as an invariant of M? Right? What good is it? So of course we have some partial answers from earlier today, which is it detects free summons. But there's also a bunch of research saying that if you think of all the rings between R and its integral closure in the total quotient ring, the trace ideal determines the rings over which your M is a module. Right? So one result of that type is talking about how it relates to centers of endomorphism rings. So if M is reflexive and faithful, for example, you have an identification between the center of the endomorphism ring and the endomorphism ring of the trace ideal living inside the total quotient ring. Right? So free summands may be centers of endomorphism rings, but of course, there's so much more that one could do. This is kind of open. Question. Given a ring, can you tell, can you determine or characterize all the trace ideals? Right, pretty natural question. You have a ring, which ones are the trace ideals, which ones aren't? In general, we don't know. In general, we don't know. There are some cases in which we do know, one of which I mentioned earlier today, so I'll just rewrite it here. In Artinian and Gorington rings, all ideals are trace ideals, which is kind of just a crude measure. Okay, what if all of them were? What do we know, right? But any more granularity, it's actually quite difficult to tell. Some people have worked specifically thinking about this over semi-group rings, and so there are some characterizations there. There's some characterizations for very simple rings, like regular rings and things like that, but largely this is wide open. Okay. Question. What useful properties does a trace ideal have? Some of those we've been through over today, right? The ones that I've explained were actually like very simple to establish. So if someone more sophisticated came along, maybe they'll be able to tell us some more things about what properties they have. In this direction is one that I also mentioned earlier today, is general non-rigidity of trace ideals. So I'll just write what that means here. Say x1 of the trace is not always, but is generally not 0. And that accounts for the use of trace ideals in attacking the rigidity conjectures. So for example, that paper by Hunicke, Angar, and Wiegand that I talked about at the beginning of this talk, they liberally use trace ideals in their attack of that conjecture, and other people use it similarly, right? Question, second to last. Can you fruitfully generalize to modules? Okay, so there's an obvious way to do this. So if M is living inside of X, we can define the trace module of M in X to just be, take all the images of homomorphisms from M to X, some of the images, and then that's going to be a submodule of X, right? Just the same definition. However, for any M, M is the trace module of it in itself. It's also the trace module of R in it. So like, is this useful? Unclear, right? But however, if you restrict your attention to proper trace modules, So for example, the trace module of M and X, which is a proper submodule of the ambient module X, those classes of things are very interesting and have interesting properties. Okay. And the very last question, does the set of trace ideals have interesting algebraic properties or other properties? So instead of looking at individual trace ideals or trace modules, look at the full set, fix an R, look at the full set of trace ideals over a ring. Does that have interesting properties? So people have explored when it's finite. So there's a paper by Eleanor Faber that talks about when this set is finite and linking it to the representation theory of certain rings, right? You can also know that it exhibits some closure under closure operations. So for example, if I is a trace ideal, so is the radical, so is the double dual, sorry, so is the double annihilator, so is the double dual, so is the integral closure, et cetera, right? And so this has been used, for example, in a paper been in Hai Long Dao to basically determine the representation theory of ARF rings using this particular fact, for example. So I think it's good to just leave with these open questions, right? So there's a bunch of directions and people working on this, including a number of people in this room. So I hope that this gives you a good introduction. Thank you for coming.
Awesome. Are there any questions for Haydee?
Oh, what's up?
I found this really useful because I always struggle to find out where to look at these facts. Where are good places to look up facts about trace ideals?
Which facts? It depends.
Yeah,
What kinds of facts are you looking for?
basic structure facts.
Basic structure facts.
And good references.
So trace ideals have been in literature for a really, really, really long time, right? So if I were to like go OG, I would think the like Alexander-Goldman paper on maximal orders. There's a bunch of stuff about trace ideals in the appendix, right? So in the 60s, it was old stuff, right? They're maximal orders. So the appendix has a bunch of stuff on trace ideals. But they tended to, it's about Alexander and Goldman, and they tend to focus on trace ideals of projectives and things like that. So maybe not so interesting to a modern eye. Also dealing with trace ideals of projectives is Herbera out of Spain. But then there was like kind of a gap. And then now there's kind of a modern resurgence of interest in trace ideals, right? And so like, I hate to reference my thesis paper, but you know it, right? And so I collected a few facts about trace ideals. Also at a similar time, Herzog, Samate have a paper that does something similar. And then since then, there's just been like a lot of places that have highlighted that. So like we can talk later if you're looking for something in particular. But
No, I can't be like, I'm sure this fact is known and I know where to find it.
sure. We can talk.
Cool. Well, maybe if anyone in the room has further questions, we can chat later. But before we like leave, does anyone on Zoom have any questions for him? All right, cool. Let's thank Haydee again.